In this video, I'll provide an introduction to the Naïve Bayes classifier. I'll provide an overview and some background intuition, followed by a more formal definition. I'll also discuss a simple way to represent text instances using bag of words features. Naïve Bayes is a probabilistic classification method that learns to make predictions for previously unseen documents based on patterns it has learned from existing labeled documents. For example, the classifier might learn to predict either positive or negative labels for spans of text. There are several variations of the Naïve Bayes classifier that can be used to predict continuous, categorical, or binary outcomes. I'll be focusing on multinomial Naïve Bayes in this video because it's more common and it's also just a generalization of binomial Naïve Bayes. A multinomial Naïve Bayes classifiers make simple classifications based on Bayes' rule. You can use any kinds of features that you want with these classification models, but traditionally one type of feature included is the bag of words representation, which we'll talk about a couple slides from now. Naïve Bayes is named as such because it really is sort of naive. It just assumes that all features are independent of one another, and that's that. In practice, that's usually not the case in natural language processing. We already saw with language models that which words appear generally depends on the context. However, in spite of this, Naïve Bayes classifiers still tend to perform reasonably well on a large variety of tasks. The actual equation for predicting a label using a Naïve Bayes classifier is really simple and is shown on the slide here. And basically, for a given document or text instance, you find the probability of each class occurring given that text instance, and then you return the class that maximizes that equation. Since getting the probability of a class occurring given the text instance is easier said than done, the classifier uses Bayesian inference to compute its probabilities. You've probably seen Bayes' rule a bunch of times, but in case you haven't, or in case it's been a while, Bayes' rule states that to predict x given y, you can just multiply the probability of y given x by the probability of x and divide that product by the probability of y. So if we take Bayes' rule and just substitute it into our previous equation, we get the new equation shown here. Even though the equation is already pretty simple, we can actually simplify it even further by dropping the denominator. And that's because the probability of the instance occurring doesn't change for each class. It stays the same every time. So we end up being able to predict a class by just computing the probability of the document given the class times the probability of the class for each possible class, and then selecting the class that maximizes that equation. A lot of times you'll hear people refer to the two components of this equation as the likelihood, that's the probability of the text instance occurring given the class, and the prior probability, which is just the probability that the class occurs in the training data in general. Now, like I mentioned previously, a common way to represent text instances when doing Naïve Bayes classification is by computing the bag of words representation. A bag of words representation is just a collection, a bag, if you will, of all the possible words in a vocabulary, with frequency counts indicating how often each word occurs in the current text instance. This representation makes the huge simplifying assumption that the order in which the words occur in the text instance doesn't matter. More formally, if we were to take a bag of words representation for a vocabulary of size n, represented as the set of independent features f1 through fn, and substitute it into our Naïve Bayes equation, we would end up having the probability of that set of features given the class times the probability of the class occurring in general. Since we're assuming that features are independent of one another, we're able to just multiply the probabilities for each individual feature together when deciding which class to predict. So the probability of features 1 through n occurring given class C is equivalent to the probability of feature 1 occurring given class C times the probability of feature 2 occurring given class C, continued all the way up until the probability of feature n occurring given class C. And this brings us to the final equation shown here, where the predicted class label is the class label that maximizes the equation where we multiply the probability of class C by the product of the independent probabilities of all features given class C. So we know the theoretical details about naive Bayes now. How do we apply it to a practical scenario? To use a naive Bayes classifier, we simply take our test instance and split it into tokens. We extract a vector of bag of words features based on those token frequencies, and then compute the probabilities for each of those features given each class. For a given class, we multiply the relevant likelihoods by the prior probability of the class, and after doing that for each class, we select the class that maximizes that equation. If we want to increase speed and avoid generating numbers that are too small for us to accurately represent, which can happen when you multiply a lot of small probabilities with one another, we can do these computations in log space. If you choose to do that, just remember to add things together instead of multiplying them. In fact, when you do this in log space, you end up predicting your class value as a linear function of the input features. This means that naive Bayes belongs to a set of classifiers referred to as linear classifiers. All this means is that they make their decisions based on a linear combination of inputs. Later this semester, we'll see some examples of text classification using nonlinear classifiers as well.